Okay, finally, part C. Now, I left you at a cliffhanger saying that at the end of part B, we would prove Cardano's formula in the end. We're finally going to get there. Now, if you recall, we get that alpha and beta through that horrible quadratic formula substitution is one of these expressions, this either plus or this minus, and then we do minus alpha minus beta from this factorized form. You take only one of them. Now we only care about this factor here because this is a real number root. Because remember, this omega 1 alpha, omega 2 beta, and omega 2 alpha, omega 1 beta are basically, yeah, I guess alpha and beta are numbers related to the real roots or real numbers, which are weighted by complex numbers. So these are complex roots. These two are complex roots. And we can't show them in our typical R2, Rn, R3. Yeah, we can't show them in x to R2 unless you extend to the Argon diagram. So these we're going to ignore, and this purely just covers this factor over here. So we have this, and then what's left is, it asks us substituting s equals minus 3p and t equals 2q, prove Cardano's formula, which is essentially this thing. Because now you go and rewrite, let's see, s over minus 3 equals p, and t over 2 equals q. And then you plug it into this ugly mess here. So now I get minus cube root t2 plus t2 squared minus s minus 3 cubed minus t over 2 minus, oh wait, no, that's just an erased part, minus t over 2 squared minus s over minus 3. Wait, am I just repeating? No, this is right. It's just the exact same thing except with a minus and a plus here. And then that's it. This is essentially like Cardano's formula in its best form. And it's a bit ugly with the nested radicals, but I like that you have basically a half and a square here for like these terms here, and a cubed and a divide by a third over here. Just to get to match what the IB has, or Revision Village has for this particular problem here, all they just did afterwards was go and did the squaring and cubing of these things to get the final result. So they just did, oh yeah, remember, this is the root, so if we go and make this positive, this will just be a factor. So it's basically positive this. So opposite sign junk here. We get plus, so now it's cube root of t over 2 plus square root of t squared over 4 for a cube, that's minus minus, so that becomes a plus. Negative 1 to the 3 becomes negative 1 to the 3 is negative 1 because 3 is odd, so that's a negative times a negative, that becomes a plus. So we get plus s over 27 s cubed here. And then we get the other same result, cube root. And everything else, just except for the plus sign here, we get a minus sign here. Oh god, yeah. And that's it. That is Cardano's formula. The depressed one. Remember, this is just for the depressed one. Because the general one is even more hideous. Unless my memory is mistaken or the like. But unfortunately, we are not done. We have now 2 problems left, and that's to go and apply this result, this formula here, for a specific cubic polynomial, and then do it for a shifted solution. So, number 2, use Cardano's formula to show to find exact solution for x cubed plus 6x plus 5 equals 0. Again, this is a depressed cubic here. And this is just like direct substitution into the result of our answer, because the S and T are different here. So yeah, basically in this case, if we follow it for like this form here, our S is 6 and our T is 5. So then we just have to plug that directly into what we get for the formula here. So then root 1, which is alpha plus beta, is cube root of minus 5 over 2 plus square root of 25 over 4 plus 6 cubed over 27 plus cube root of minus 5 half minus square root of 25 over 4 plus 6 cubed over 27. Okay, and then the rest is just a bunch of canceling here and there and so forth. For this number here, 6 cubed over 27, I basically have to do some calculator work here, and you're allowed to do that. That's basically the same thing as 8. But we want to put into a common denominator with this 4 over here. So I'm going to write this 8 here as 32 over 4. And then we get the exact same thing. So we get 25 over 4 plus 32 over 4. If you do that with a calculator, you'll get 57 over 4. So in the end, this root here will be equal to cube root of negative 5 halves plus square root of 57 over 4 plus cube root of minus 5 halves minus square root 57 over 4. Done. And now the last problem, which is insane that they're, actually it's just a plugin. So like this one isn't too bad. The next one, which is still an application, requires a bit of work. So now, number 3, using z equals x minus 1, so this substitution here for a complex number, find solution for z cubed plus 3z squared minus 6. Again, the s is free, the t is minus 6 for this thing here. And all you have to do is just plug in x minus 1 to here and to here. X minus 1 cubed plus 3 times x minus 1 squared equals 6. And now you either have 2 choices. You either do overkill and apply the binomial theorem, or you go and use Pascal's triangle now, because these are fairly small powers, so this is easy to do. So again, Pascal's triangle, you start with a 1, then you have 1 along the diagonals here, 1 plus 1 gives you 2, so 1, 2, 1. 1 plus 2, add another 1 here, then 1 plus 2 here gives 3. 2 plus 1 gives 3. And then another 1. And let's see. Yeah, it's a cubic, right? So we only need to end up using this row here and this row, which will give us the binomial coefficients. Then you just need to know that with the binomial theorem, this will be going starting at x cubed and going downstairs one step at a time, whereas this will be going upstairs one step at a time. And it's being weighted by the binomial coefficients. Yep, so then I get x cubed, this here is x cubed, plus free from that there, then x squared, then minus 1, plus 3 times x times minus 1 squared, plus minus 1 all cubed. And now we have this term here, so then that's plus 3, and then all of this has to be boxed in here. You could just expand this by a quadratic if you want. So that's x squared minus 2x plus 1. And I also want one end of the term to be, so it equals 6 here, but I'm going to minus 6 on both sides. So that we can end up with one term being equal to 0. So that we can officially factor this. Let's see, and all that stuff here gives us x cubed minus 3x squared plus 3x minus 1 plus 3x squared minus 6x plus 3 minus 6 equals 0. We get some cancellation magic. This gets destroyed, this gets destroyed. This 3 minus 6x becomes a minus 3x, x cubed minus 3x, and this 3 minus 6 becomes, wait. Oh, I'm sorry, because there's a minus 1. We have a minus 1, a 3, and a minus 6 here. Minus 3, minus 1, minus 4 equals 0. So then that means our new, once we shifted this around, our new s and our new t is going to be s equals negative 3, t equals negative 4. I'm going to save this now. I'm going to go and delete this stuff here. Pain, 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 especially since that's near the end of the stuff. And now we just get R1 equals cube root of negative 4 over 2 plus square root of negative 4 squared over 4 plus negative 3 cubed over 27 plus cube root of negative 4 over 2 minus square root of negative 4 squared over 4 plus negative 3 cubed over 27. Just do the algebra stuff. You get cube root of 2 plus square root of 4 minus 1 plus cube root of 2 minus square root of 4 minus 1. This gives us cube root of 2 plus square root of 3 plus cube root of 2 minus square root of 3. Okay, screw this problem. We are done. We are done. That's it. That's all that was needed in the end for this. And that's it. That's basically the entire packet covered at this point. Once again, I mentioned that this weird factorization here is a result from Galois theory. I had time to look at the stuff, and it has to do with a field automorphism, because auto means self. So basically these complex number roots in the triangle here are being rotated by themselves as you multiply them. They kind of map to themselves over and over again. And again, you can go and look at like that video if you want in the end. But yeah, just to emphasize again, this is a really good problem to review everything in the IBAAHL math syllabus, but it is not a good prediction of what an actual paper-free question will be like, because you have 2 questions, and this is still one, and this clearly took way too long for what it's worth. We can even see how long the time for this video is. But yeah, that's it. I hope you enjoyed the time. Until then, I'll see you in the next video. Stay tuned. Thank you. Bye-bye.